going to start with the next talk. The next speaker is Professor Arnaud Beauville from Nice, France, and he's going to talk us about vector bundles on Fano threefolds and K3 surfaces.
Okay, thank you for the invitation. Some of you know that I have very strong ties with Chile. I mean, I taught in Santiago almost 50 years ago. Of course, at that time, there was essentially no mathematics in Chile, at least no at research level. And I must say, I'm very pleased to see the development of mathematics in Chile, in particular of geometry. And I think this new research center will be extremely important for the development of geometry and more generally mathematics in Chile. So, okay, let me start the talk. So the setup will be the following. I have a complex Fano threefold X. That means that the canonical bundle, or let's say the inverse of the canonical bundle, Kx minus 1 is ample, is very positive. If you are not adheres with the definition, just think that this is the simplest possible algebraic varieties. For instance, we could look at the cubic hypersurface in P4 or quartic hypersurface or intersection of two quadrics. And these are the algebraic varieties which, with a very rich geometry. Now, what I want to do is to take a sort of a hyperplane section of this X, namely, I take a surface in the linear system Kx minus 1. This system is ample, so it should have a lot of, contain a lot of divisors. And in fact, one can prove that it always contains a smooth divisor, so a smooth surface, S. And by what is called the adjunction formula, this S will be a K3 surface, as we saw in the previous talk. Namely, the canonical bundle is trivial, and it is simply connected. Now, suppose the question I want to consider in this talk is the following. Suppose I have some nice moduli spaces or vector bundles on X, and I want to, so that I can restrict to S and get a new moduli space, MS. The question is, what can we say about this restriction map? Now, you should know and keep in mind that we know very little in general about moduli spaces or vector bundles. Even on projective space, I mean, it's amazing how little, I mean, we don't know if there is a rank 2 vector, non-trivial rank 2 vector bundle on projective space, at least where the dimension is at least 5. I mean, we know really very little. So, I mean, I would not expect that we can say something interesting about that. But we can, and it is a very nice observation of Andrei Turin 30 years ago. The point is that for the K3 surface, for the surface S here, we have a very interesting property due to Mukai. Namely, first of all, it's smooth, and it has a holomorphic symplectic structure. This means it's like a real symplectic manifold, but in the holomorphic setup, that is, we have a closed two form, sigma, which is non-degenerate at every point. Let me explain how we get this symplectic structure, because it's quite simple. For a vector bundle A in this moduli space, it's well known, I mean, by deformation theory, that the tangent space to the moduli space at E is this cohomology space, H1 of S, with a value in the endomorphism bundle N of E. Now, we want to define a bilinear form, alternate bilinear form on this H1, we just take the cut product. This goes into H2 of endomorphism of E. And then we use a trace, which is a bundle map from end E to OS to get something in H2OS. Now we are on a K3 surface. H2OS is dual to H0 KS, which is one-dimensional. This is C. So in this way, we get a bilinear form. It is easy to see that it's alternate, and it is non-degenerate by third duality. So moreover, we can prove that it is closed. It's a small computation, which is that this gives a symplectic structure on this moduli space. This is very particular to K3 surface. I mean, you don't think that this is a general fact. Okay. Now this is very interesting because in many cases, this this moduli space MS is compact, is smooth and compact. Hence, it is a projective hyperkähler manifold or projective symplectic manifold. I'm starting from a, I mean, remember that S is lives in a Fano varieties, and for it's a projective manifold. Therefore, this moduli space is also a projective manifold. So projective symplectic manifold are sort of generalizations of K3 surfaces that again carry a holomorphic projective, holomorphic symplectic structure and holomorphic two form, which is everywhere non-degenerate. And these manifolds have very interesting properties, and they've been intensively studied in the last decade. There are plenty of work on this. So, okay, an important feature, I mean, using this symplectic structure is the presence of Lagrangian subvarieties. So that means that we have a subvariety of this moduli space, such that for the smooth point, I mean, it might be singular, but outside the singular locus, the tangent space is a Lagrangian subspace in the sense that it is isotropic and of maximal dimension, namely the dimension is half the dimension of the whole space. This is a Lagrangian subspace of Tx of M, and this is what is called a Lagrangian subvariety. These are quite important in the study of hyperkähler manifolds, in particular the fibration, where the fibers are Lagrangian subvarieties, have been much studied in the recent years. Now I can explain the result of the remark of, it's an observation of Turin. So let's go back to now we have this surface S, which lies in the Fano threefold X. We look at the restriction map from this moduli space on X to the moduli space on S. And the theorem is that if we assume this vanishing H2 of X with in end of E 0 for all E in MX, we know that MX is smooth, and this restriction map is a local isomorphism onto a Lagrangian subvariety of MS, which I will call in the future a Lagrangian immersion. It's an immersion. I mean, it's not always an embedding, but it's an immersion, and the image is a Lagrangian subvariety. This is a very nice remark because it provides a lot of examples. As we will see, it provides a lot of examples of interesting Lagrangian subvarieties in projective hyperkähler manifold. Well, about examples, I have to say that this theorem, I heard actually Turin explaining this, and I think it was in Erlangen in 1990. And maybe Bayreuth, sorry, Bayreuth in 1990. He wrote a preprint, it was never published, but he sort of states this theorem in passing. I mean, he mentions this result, and then he goes to other things. He doesn't give any example where this condition holds. And I must say that when I saw this result, I think it was nice, but I said, how do you prove something like that? How do you prove such a vanishing? And you see, you are on a threefold, so third duality will be of no use. It will be an isomorphism with some H1. Even if you know a specific vector bundle, it's quite hard to prove something like that. So at the time, I mean, I thought there was no use for this theorem, and I sort of forgot it. And so this is a problem. How can you prove something like that? Recently, actually, for some reason, I mean, by doing other things, I came back to that. I realized that you can give a number of examples. But let me first show you the proof of Turin's result, because it's quite simple. So we start from the exact sequence. You see, OS is a divisor in the linear system K minus 1. Therefore, it is given by the vanishing of a section of X minus 1, which we can see as an homomorphism like this. And OS is just the cokernel. So we have this exact sequence. Now we take we tensor this exact sequence with the vector bundle end of E, bundle of endomorphism of E. So we get this sequence where here by ES, I just mean the restriction of E to S. I tensor with OS, so this is what I get. And now we take the long exact sequence in cohomology associated to this short exact sequence. Now we have some vanishing. Our hypothesis that H2 of end of E is 0. By third duality, this means also that H1 of this here is 0. So let's start with H1 here. This is 0. We have H1 end of E, H1 end of ES, and then H2 of this, which again, we use third duality to say that this is a dual of H1X end of E. And then we have H2 end of E, which is 0 by hypothesis. So we get this short exact sequence where you see we have one vector space here and it's dual here. Now, remember that this H1 here is a tangent space to MX, the moduli space on X at E. And similarly, this is the tangent space at ES of the moduli space of the bundles we consider on S. So first of all, this tells us that this is injective. So this is why we have this immersion property. Also, we see that the dimension of MX is half the dimension of MS because we have the same dimension here, and the dimension here is twice the dimension of each factor. Finally, the only thing we have to prove is that this image here is totally isotropic with respect to the symplectic form here. Now we look at this diagram here. This is, remember that this is how we prove we should write on we should look at the first at the right hand side. Here, this is remember this is the definition of the symplectic form on MS. Now this comes. We look at the image of H1 end of E, and so this factor through H2, which is 0 by hypothesis. So this tells us that when we restrict our symplectic form to the subspace image of H1X end of E, we get 0, which is exactly saying that this subspace here is isotropic in symplectic space. Since the dimension is half the dimension, it's a Lagrangian subspace, and this shows that this assertion about mx being Lagrangian in MS. Okay, now as I told you, I mean, my goal in this talk is to show you many examples where this applies and where we get nice Lagrangian varieties in this projective symplectic manifolds. So the idea is to use Serre construction. This is one of the very few construction we have to get non-trivial vector bundles on a given manifold. I will just do it in the case I'm interested here. So X is my Fano threefolds. I suppose that I have a smooth curve, C. Well, it could be a local complexity section would be enough, but let's say C is smooth. And the assumption, the key assumption, is that the canonical bundle of C is a restriction of a line bundle of X. This is, of course, not automatic. I mean, this is a hypothesis. And moreover, I want to be this, I want this line bundle here to be more positive than the canonical bundle, which is negative. I recall you because I'm Fano, so it's not a very strong condition. We want to write it at Kx tensor L for L ample. Then this implies, this is essentially Serre construction, that there is a unique extension of this type. So we take the ideal of C in X, we twist it by this line bundle L, and we get an extension by OX, which turns out to be a rank 2 vector bundle on X. With following property, its rank is 2. Essentially, by construction, if you look at this exact sequence, the zero set of this section S is the curve C. And if we restrict E to C, we get the normal bundle of C in X. C is codimension 2 in X, so this normal bundle will be a rank 2 vector bundles. And essentially, by construction, it's a restriction of this vector bundle. So this is a very useful way to get, at least for rank 2, to get rank 2 vector bundles on a variety. And now here's my main result. I mean, which is not difficult, but this is a key observation. The basic hypothesis will be that each one of these normal bundles, so this is we have this curve C in X, and we assume that each one of the normal bundle is. And then we have some technical hypotheses here, which in practice will always be verified. I mean, they are not very important. In all the examples, it will be automatic. So we want this surjectivity of these two restriction homomorphism here from X to C. Then what is the conclusion? Well, first of all, we have then the rank 2 vector bundle here that we have just constructed has this vanishing property. And second, we have a sort of very nice situation. If we deform C, I mean, we look, the curves like C are parametrized by something. This is called the Hilbert scheme in X. So we have a nice variety which parameterize all possible deformation of this curve C. To each curve of this type, we associate a vector bundle by this construction. So we get a map from this parameter space of curves to the parameter space of vector bundles. Well, under this hypothesis, this map is a smooth map, and moreover, the fiber of a vector bundle E in MX consists essentially of the section of H naught of E up to a scalar. We have seen, you see that if you take a section of E you get a curve of the same type. So it's not surprising that, that we get all the deformations of C in that way. It's open because there could be some nasty phenomena where the section could vanish along something of codimension 1, or but well, in practice, this will be, we will get usually the whole projective space here. So there is a very nice relation. What you have to remember somehow is we have this very nice relation between this the curve C. The curves will be very simple in the example. We take line, conics, things like that. And so we know very well how to parameterize them. And this gives us a nice parameterization of this moduli space MX. Okay. Let me give just an idea of the proof. The proof is not difficult. We look at this exact sequence here, this extension, and we take the tensor product with E dual. Now here's the determinant of E will be L, right? It's by this extension here. So this since this is a rank 2 vector bundle, the E dual is isomorphic to E tensor L-1. So we tensor by this. So here we have E dual. Here we have E tensor E dual, which means end of E. And here we have IC E dual tensor L, which by this property here is just ICE. Now from this, we want to prove that this H2 in the middle is 0. This is very stupid. We just prove that H2 here is 0 and H2 here is 0. You combine exact sequences, and this is sort of straightforward, not difficult. So this is to prove 1 actually, and to prove 2, this follows, this is a sort of standard using deformation theory. It's deformation theory tells us what is the tangent space to this parameter space here. We know what is the tangent space here. We know what is this mat between tangent spaces. We just have to prove that it's surjective, and this follows from the hypothesis. So this is not difficult. Okay, the rest of the talk will just be devoted to examples. And now I should say I want to take the most simple, possibly most simple situation. I don't want to enter into technical details, so I will really try to look at the simplest examples. And as you will see, I hope they are already interesting. So I will sort of restrict my hypothesis. I will assume that X is embedded into some projective space. So that the Picard group of X is just generated by this embedding by OX of 1. Then the canonical bundle will be a multiple of is, because I have no choice in the Picard group. So since it's negative, it will be on the form OX of minus I is called the index. And I will take 1 or 2 because 3, it's well known, at least for the experts, that with I equals 3, you just get a quadric, and with I equals 4, you get the projective space. So these are not so interesting. I will restrict to index 1 or 2. And then let me briefly recall the classification. Classification of Fano threefold goes back to Fano first, but have been completely rewritten in modern terms by Istovsky. So index 2, we just, with this strong hypothesis, we just have 3 cases. The cubic threefold in P4, the intersection of 2 quadrics in P5, and the degree 5 threefold in P6, which is a certain intersection, linear hyperplane sections of Grassmannian. Index 1, we have more. the traditional notation is x 2g minus 2 in pg plus 1, and g could be between 3 and 10 or equal to 12. The first example are quartic threefold in quartic hypersurface in P4, intersection of a quadric and a cubic in P5, intersection of 3 quadrics in P6, and etc. So we have a small number of very interesting varieties with a very rich geometry. Now this line model L, remember that what we want is this. We want that K, the canonical bundle, should be the restriction of Kx tensor LC, and L should be positive. So again, because our hypothesis on the Picard group, L will be of the form OX of J, and J should, because this J should be 1 or 2. I mean, it's easy to see that that's the only possibility. Then you see that Kc is OC is a restriction to C of O of J minus I. And in fact, we have these three possibilities. J minus I can be minus 1, 0, 1. And so let me make a list. First case, so index 2, J is 1. This implies that C, first of all, the index is 2, so we are in one of these varieties here. And I claim that C should be a conic because C, you see, Kc should be O of OC of minus 1. So first of all, it should be negative, which means that C should be a P1. But if we want, on P1, the anti-canonical line bundle has degree 2. So we want that O of 1 restricts to something of degree 2, which means that C should be a conic. In degree 2, so second possibility is that I is J, or it could be 1 or 2. This means that the canonical bundle here is trivial. It's just, yeah. Which, so of course, C is an elliptic curve. And since J equal I, L is OX of I. So we have in fact two sub-possibilities. OX of 1, X could have index 1 or 2, and then L is given by OX of I. And the third possibility is that I is 1, J is 2, so Kc is OC of 1. This means that Kc is induced by the embedding of X, which means that C is a canonical curve. C is embedded in this. We are in this situation here, index 1. We're in PG plus 1, and C is a canonical curve embedded by its canonical system in PG plus 1. So that's the three possibilities which I will consider. Moreover, to simplify, I will assume that also for S, the Picard group is generated by O of 1. We know that this is true if S is taken general enough in each case, so that will be good for us. And then this has a very nice consequence that both the vector bundle E and its restriction to S are stable. For E, in fact, that depend only on the hypothesis on X, but this hypothesis makes that we are sure that the restriction of E to S is stable. Therefore, we have a nice moduli space of stable bundles of E, which restrict to nice stable bundles on ES and on S, sorry. And so we have a very no problem to define the restriction map. Okay, so let me start now with the example with the first case. So this is, if you remember, we should look at conics in index 2 Fano threefolds. So again, we have xd in pd plus 1, d is 3, 4, 5, not much choice. K is O of minus 2. Kx is a definition of index 2. The surface S is in k-1, which means that the intersection of X with a quadric, and the line bundle L is O of 1 and C is a conic. Okay, now here's a proposition. Well, in all these cases, our basic condition, vanishing of H1, is fulfilled, and the dimension of mx is 5 minus d. So I said it's a warm-up because you see the dimension will be very small. It's not, in some sense, it's not very interesting, but it's still non-trivial. So this is why I start with this. So first case is d equals 3, and this means that we have a cubic threefold in P4. Then it turns out that mx is isomorphic to a very famous surface, f of x, called the Fano surface of lines containing x. So how do you see that? Well, when you have a conic on a cubic threefold, you look at the plane spanned by that conic, and it intersects the cubic. It must intersect the cubic along a degree 3 curve, which means that you have the conic plus another line, the residual line. So the map we had before from the space of conics to mx, to this f of x, is just the map which associates to a conic, its residual line. It's not, I should say, it's not trivial. There is one point which is where we have to prove something, namely that you know that you have your vector bundles on the cubic. You have this description as by circumstruction. You know that one section gives a conic, so all sections, at least in an open subset, will give conics. But you have to prove that all these conics correspond to the same residual line. They are just cut out by the pencil of planes. Is this passing through the line? The net of sorry, it's a dimension 2 net of planes, and this is non-trivial. So this is for X. So what about S? Well, MS is what is called the Hilbert scheme S bracket 2. This is, you should think essentially, if you don't know that, this is a well-known example of a holomorphic symplectic projective manifold. You can think of that as the space of pairs of points in S. 2 means just take 2 points. The only point is that you have to be careful when the 2 points come together. You have to keep somehow the, you just don't want 1 point. You want really something a little more complicated. But you know, it's fine to think of it as just the space of pairs of points of S. And the restriction map is just the following. If you have a line here, now S, remember that S is the intersection of X with a quadric. So you take a line, you intersect it with the quadric, you find 2 points, and that's our map. So it's a very simple map. It's non-completely trivial, at least I don't know trivial proof of the fact. So the result is that f of x is a Lagrangian subvariety of S2. And well, this is not a trivial result. What is it for d equals 4? Maybe I will pass this quickly because it's not very interesting. You find a curve in a surface. You see d is 4, so the dimension of the modular space here is 1. The dimension is 2. In that case, I mean, every curve is in a surface is Lagrangian, because if you restrict a 2 form to a curve, you find 0. So it's not a very interesting result, but still there is a nice situation which I describe roughly, but maybe I will you see, maybe I will pass on that because time is short. And finally, for d equals 5, we find just an isolated point. And in that case, there is just 1 point, which is, in fact, as I said briefly before, this X5 is obtained by taking a linear section of this of the Grassmannian G25. This Grassmannian carries a natural universal quotient bundle, and this is this guy that we find on X and on S. Okay, so let me pass to something maybe a little more interesting. So the next case is when we pass to elliptic curves in index 2 Fano threefolds. So for a reason, I mean, in part for having the surjectivity, which I briefly mentioned in the proposition, it's convenient to assume that C is what is called a normal elliptic curve in the CD plus 2 in PD plus 1. That means that C is embedded by the complete linear system of degree D plus 2. So remember D is 3, 4, or 5. So it would be a quintic elliptic curve in the cubic in P4, or a sextic curve in P5, etc. Okay, then we have this properties that L is O of 2, the extension that we are interested, the vector bundle E is constructed in that way. Again, this is the index is 2, which means that the surface S, which is in K minus 1, is the intersection of XD with the quadric. So here's a proposition. Well, first of all, every XD contains an elliptic curve C D plus 2. See, this is not trivial at all. You have to, if you want to say something non-empty, you have to prove, first of all, that your Fano threefold contains a curve of the type you are considering. And this turns out to be true here. Now, if you have such a curve, you can construct your bundle E. And it's a very nice vector bundle. It is what is called a Ulrich bundle. This is, I mean, usually it is defined by this vanishing condition. The whole cohomology, including H0, H1, H2, H3, should vanish when we twist E by -1, -2, -3. So this is a very strong vanishing condition. It's not difficult to see. That is equivalent to say that when we see E as a sheaf on the projective space, it has a very nice resolution by vector bundles on the projective space. We just have this OP, some multiples of this canonical bundle OP of 1, and the maps are given by matrices of linear form. So we pass from O of -D to O of -D plus 1. This means that this is given by matrices of linear forms. And so this is and the third result is that, again, we find the vanishing that we need on each one, and therefore the restriction map is a Lagrangian immersion. And what is nice now is that the dimension, curiously, does not depend on D. The dimension of the modular space Mx is constant, equal to 5, and the dimension of Ms is 10. And now I have to say something. It's very hard to find examples of holomorphic symplectic or manifolds. For a long time, there was only 2 series of examples known. One is this Hilbert scheme that we saw already for S against free surface. There is also an analogous construction starting from abelian surfaces. And it's after, I don't know, 10 or 15 years, then Kieran O'Grady found 2 exotic examples. Exotic because they are sort of isolated, maybe I should say sporadic rather. There is one of dimension 10 and one of dimension 6. And it turns out that this one of dimension 10 is exactly birational to classical. Now people use notation OG10. This is special projective symplectic manifold found by O'Grady. So it's quite interesting because this is a complicated object. I think it's nice to find some Lagrangians of some simple Lagrangians of varieties inside this these objects. Let me give a short ideas of the proof. So this, I just repeat the proposition here so you have it. How do you prove one? How do you prove that, let's say, think of the cubic threefold, for instance. How do you prove that every cubic threefold contains a quintic elliptic curve? Well, this is not trivial, but what is easy is to prove that it contains a quartic elliptic curve contained in a hyperplane. Because if you take a general if we intersect x, let me do the argument with d equals 3. It's more concrete. So if you take a hyperplane in a cubic threefold, you get a cubic surface, and you know very well the curves on a cubic surface. In particular, it's quite easy to prove that a cubic surface always contains smooth elliptic curves of degree 4, smooth quartic elliptic curves. Now you take this quartic elliptic curve, and you take a line which gets out of your, so maybe you can see me. So you have the hyperplane here cutting your elliptic curve, and you take something which is perpendicular somehow, which goes outside of this hyperplane, but which meets the curve CD plus 1 at one point. This is again, a singular elliptic curve, and there is a sort of standard deformation theory for these curves, which tell you that indeed this deform into a quintic elliptic curve in the cubic threefold. Part 2, it's actually not difficult, so you have to prove these vanishings, and you just use this exact sequence which defines E, and this is, for instance, you know very well the cohomology of OX. You know well also the cohomology of IC because everything is quite explicit. It's not difficult to get that this vanishing. The third part is maybe not so trivial, but it's not difficult either. The point is that we use third duality. H1n of NC is by third duality. This is I put an isomorphism. Actually, I forgot to put a dual here, but this is the dual to H0, K-C tensor, NC dual. But we are on elliptic curve, K-C is trivial, so it's just H0 of the dual normal bundle. And if you remember the normal bundle in this construction, the normal bundle is just induced by our vector bundle E. So we have to prove that this dual has no sections. And the point is to use the linear resolution that we had before, because E is a Ulrich bundle. And so this gives you a resolution in the other direction. I mean, this gives you an exact sequence, a presentation somehow of E star. And using that, you show that there is no global section. And the rest follows from the proposition. Now, ES of -1, so you see E, first, because of this extension, when we can look here, again, this shows that the determinant of E is O of 2. So the determinant of E of -1 is trivial. And then same if we restrict to S, ES of -1 has trivial determinant. You can compute the C2, EF and C2-4, and that's exactly how O'Grady defines this, at least birationally, this holomorphic symplectic manifold of dimension 10. It takes the moduli space on a K3 surface of vector bundles with these properties. This is singular, but he defines a desingularization. This is quite a work, but does it. And it turns out that the desingularization is a holomorphic symplectic projective manifold. So we get something here by rational to this OG10. Now let me pursue this example in particular with the cubic threefold. This, if you remember this linear resolution that we had, I mean, now for a cubic threefold, we just have a hypersurface, so the resolution has just two terms, it's just of this form. And it turns out that you can take the matrix of linear forms, M here, to be skew symmetric. Now, a priori, the E, I mean, X is the support of this sheaf E, this is where the matrix M is not of maximal rank. So this is given by the determinant. But since M is skew-symmetric, the determinant is the square of the Pfaffian and the Pfaffian of degree 3. You see, it's a 6x6 matrix of linear forms. So the determinant has degree 6, the Pfaffian has degree 3, and the cubic X is defined by this Pfaffian. Now there is nice result due to these people, Iliev, Markovic, Kumirov. The moduli space Mx that we are considering is birational to what is called the intermediate Jacobian of X, which is a very important abelian varieties associated to the cubic threefold. Remember that Mx has dimension 5, and this is indeed the dimension of Jx. In fact, there is a more precise result, which I won't need, but I'd like to mention it due to Stéphane Druel, which says that all these moduli spaces always have nice compactification using no longer vector bundles, but torsion-free sheaves and semi-stable torsion-free sheaves. Here are the canonical compactification, and he can describe exactly, this is in fact isomorphic to the intermediate Jacobian with this Fano surface, which embeds blown up. The Fano surface embeds into the intermediate Jacobian, and this is a very nice description of the moduli space. But again, I won't need this refine. Right? Now, I want to change a little bit the point of view. I want to fix, I fix S. Before I had X and I was taking a divisor in a surface in X. Now let's fix S as a K3 surface, which is a complete intersection of a quadric and a cubic. So it's defined like this in P4, and consider all possible cubics which appear here, all possible F. You know, this F here is not unique because you can always replace F by, add to F a multiple of Q. This will not change the intersection. In fact, X varies in a projective space of dimension 5. So this is the space of cubic containing S, and they are of this form, constant times F here, plus a multiple of Q by a linear form. So we are in P4, so we have 5 coordinates here, plus 1 here, so this gives us 6 homogeneous coordinates, it's a P5. And the proposition now is that all this, we have all this mx with x varying here and s fixed. All these mx are Lagrangian in MS. And the proposition tells us that this is a very nice situation. In fact, we have a rational fibration here, where all the fibers at a cubic threefold is exactly this moduli space mx. which is birational to the intermediate Jacobian J of X. So you see the point that a priori, I mean, we have, when X varies, we get a family of Lagrangian subvarieties of MS, but I mean, there is no, that could vary in any possible way. In fact, there are the fibers of a very nice map from MS to some 5-dimensional projective space. And the idea of the proof, maybe I should go a little faster, is that we start for F now over the surface on S. And we do the same trick. It's again a kind of Ulrich bundle. And we have again for F a resolution of this type with a skew-symmetric matrix M of linear forms. Now this is on the quadric. Before we would say that we would do that on the projective space, but now we are on the quadric containing S. So S is a hypersurface in the quadric. But the point is that the entries are in H0 or Q of 1, and that's the same. I mean, the linear forms on Q are the same as linear forms on P4. And therefore, we can see this matrix as a matrix of linear forms in P4 and define now E as the co-kernel of this matrix. And by construction, the restriction of E to S is F, and we have exactly what we want. So let me try to make some kind of picture here. You see, we have this moduli space M sub S here. Maybe I will stop there, okay? MS. And inside of this, we have a map to this projective space, and the fibers are just the moduli space, the Lagrangian MX for all possible X containing S. Okay. Now I say there is a very nice, very recent result. This is February 2020 of Julia Saka. I said it's a rational fabric. I mean, up to now, I did everything from a birational point of view. I mean, I didn't care about completion or everything was birational. But in fact, there is a model of this MS, M prime S, which is a projective hypercolor, holomorphic symplectic, which is birational to the moduli space we had, and with a real nice, I mean, a morphism to P5, a regular Lagrangian fibration, whose fiber over a cubic X in P5 is exactly the intermediate Jacobian J of X. Maybe I will pass the idea because I don't have so much time. I should just mention that this is the extent of construction of Lazare-Saka-Voisin from last year, maybe 2 years ago. They did the same, essentially. They showed for a general cubic fourfold, we have indeed a projective hypercolor manifold with a Lagrangian fibration, such as the fiber, say, for V, when for a hyperplane which intersect V transversally, is just the intermediate Jacobian of the hyperplane section. So what Saka did is extend this to all cubic fourfold and even cubic fourfold with one node, which is the case that I was considering before. I think I will pass this and pass to now index. The last case, this is when we look at canonical curves in index 1, Fano threefold. So now we have X 2G minus 2 in PG plus 1 with G from 3 to 10 or 12. K is the canonical bundle is induced by the tautological bundle O of 1. For instance, we have the quartic hypersurface in P4, 2-3 intersection in P. When did I do it here? Sorry, this is in P5, etc. We are looking at threefolds. And we want a canonical, as I explained before, what we want a curve C in PG plus 1, which is canonical, which means, I'm sorry about the notation, but its genus will be G plus 2. You see, if you have a curve, a genus P, say, its canonical embedding is in P minus 1. So here the genus is G plus 2, L is O of 2, and if we can find such a curve, we get an extension like this. Now the proposition with a grain of salt, which I will explain at the end, is that X contains a canonical curve C of genus G plus 2. So again, we have an existence result with the properties that H1 of the normal bundle is 0. Therefore, by the general result, the restriction map is a Lagrangian immersion. And again, surprisingly, we find that the dimension of mx is always 5, and ms is always birational to this manifold OG10. The grain of salt is that for G3, which corresponding to the quartic in P4, we must assume that X is general. Let me verify the idea of the proof. In fact, what I had in the first version is the same result, but only for general X. And Daniele Faenzi showed me that a result of his and Brambilla, who give the result for all Fano threefolds of index 1. The idea is to construct directly the vector bundle E. So somehow it goes against my philosophy. You don't use the circumstruction. They do not use the circumstruction. They use a deformation theory. They start with conics, two general conics in X, as they exist, and they take some extension actually from this ideal sheaf. So this is not a vector bundle, this is a torsion-free sheaf, but there is a good deformation theory for such sheaves, and they prove that the general deformation of this torsion-free sheaf will be a vector bundle, and that it has the good properties. So I think I will not give the details, but again, this is how we do. Yeah, maybe what is it? Okay. I think I will, I don't have much time, so I think I will stop here. Thank you.
Okay. We thank Arnaud for this talk. We have some minutes for some questions. So if you have questions, turn on your microphone and ask.
Hello, I do have a question. In the case of elliptic curves in index 2,
yes,
for degree 4 and 5, do we have a description of mx or some, I don't know, Lagrangian?
Okay, yeah. You mean mx or ms?
mx, I mean the same idea to fix s and move x.
Yeah, or we don't get a Lagrangian vibration, definitely. That's well, first of all, it's let's see. Yeah, we can do that, of course, and we get a lot of Lagrangian varieties, but they do not organize into a Lagrangian vibration. It's kind of miracle. I mean,
Instead of saying Lagrangian, he said Lagrangian, the French. You know, like the French. Lagrangian.
I didn't hear. There was a question, or?
Yeah, no, I mean, I was wondering if you have a description of MX in the cases, in the case
No,
of
I guess I say in the other cases, what you have is well, you get a bunch of Lagrangian subvarieties, but they do not organize in a Lagrangian vibration. I mean, they meet each other. I mean, the situation is complicated.
Wow. Thank you.
Okay, any other question?
Just to thank you for a beautiful talk and your very long time commitment to mathematics in Chile. So thank you again.
Thank you.
Okay, we thank again Arnaud for this talk. Okay, now we have a break.